All right, here we are. We are going to solve the problem stated in the example 9.9 in the book about a closed, we can write that, it's a closed adiabatic reactive system. And as I said in the previous video, we're not able to solve this problem analytically in scipy, so we have to turn to numerical solutions. So we will start by importing numpy, and I'll refer to it as np. And the first thing I want to do is to assign values to all the parameters in the problem, because now we're doing numerics, so we need numbers. So there we are. Here we have all the parameters and constants in the problem. And I'm going to be starting a little bit backwards this time because this is new to you, so I'll try to explain the reasoning behind it as well as I can. We will be using another solver than the dsolve from scipy, because scipy can't solve it. So we'll load this solver from scipy integrate, and it's called ODInt, which means ordinary differential equation integrator. And ODInt is our new solver. And in order to find the solution, it needs three things. First of all, it needs the differential equation itself. That's quite obvious. It also needs an initial condition, so the starting value, or rather the starting values of our two unknown functions. And it needs to know the time interval on which it is supposed to solve the equations. So let's start by giving it the initial conditions, or defining them. Since we have two, we have to wrap them in a list, and I choose that the concentration should go first and then the temperature. Oops, but that's just my choice. You can choose as you like. C0, that's 500, T0 is 293. So that's the initial conditions. And then we need to specify the time interval, and that's also a list of time points. You could just write a list like 0 and 0.02 and 0.04, or whatever time steps you wanted in your solution. But it's easier to define such a list using the command linspace, which is a numpy package. Let's start with 0 and let's end with 20 minutes, just like the book does. And I choose 101 time points. So this is now a list containing 101 numbers, starting with 0, ending with 20, and equal spacing between. Right. And then, so that was y0 here and t. Now we need to specify the differential equations. And I'll do that up here, and we have to define a function. So we do that, def, and I'll call the function dy, because I refer to it as dy here. In order to compute, what dy does is that it computes the change in concentration and temperature from the present time step to the next. So we want to know how much does the concentration change, how much does the temperature change when time moves forward just a little step. In order to compute that, we need to know what is the present concentration and the present temperature. And those we will keep in a list called y. We also may need to know what the time is, but that's not necessarily the case. So this y here is a list that contains the present value of the temperature, or of the concentration and temperature. I actually want to write that down. So Y is a list that contains the concentration and temperature at the present time step. So that could be, well, to begin with, Y will be a list holding C0 and T0, because that's the initial values of C and T. But what Odient will do is that it will take this initial, these initial values to the differential equation here, and in this function here, this differential equation function, you could call it, we will compute the change in temperature, the change in concentration. And Odient will then use that to compute the next value of the concentration and the temperature. You would call that C1, T1. And we could call this Y1, and this is Y0. Then it sends these values. So Odient takes these values and put them into the dy function, which then computes the next change in concentration and temperature. Sends that back to the Odient function, which then computes the next two values of concentration and temperature. And once that's done, because we have, what was it, 101 time steps, so we end up with something called C100 here and T100. So once that's done, it takes all these, I'm sorry, did I say 101? I meant 100 here, because now we have 1, 2, 3, 100 plus the 0 here, that's 101. It takes all these and wraps them into a matrix that I chose should be capital Y. Well, I haven't done that yet, but we'll set that equal to capital Y. So capital Y is then this matrix here, containing Z0, T0, C1, T1, all the way down to C100 and T100. And that's really our solution. We can plot those, we can look at those numbers, but that's all we have. We don't have an analytical function, a symbolic result of any sort. We just have these two lists of numbers. And that's what we call a solution, a numerical solution. So this is actually our solution here. Okay, so let's try that. So the first thing I'm going to do is that I'm going to define C is the first element of Y. Remember, Y is sent from Odient. It contains two values, the two present values of C and T. So I extract those from the Y list here. And then I want to compute the change in concentration and the change in temperature. And to do that, I use the differential equations like that. You'll recognize these equations from the previous video. So now we know what the changes are, dc and dt, and we need to return those to Odient. Like that. So this solution procedure is going to be bouncing back and forth between this Odient command and this function here. And I said that I wanted to call the final result capital Y. And I also want to make a plot of that. So I'll import the matplotlib pyplot as plt. And then I'll plot I have to have two lists of numbers. The first list is my x values, that's my time points, and then I want my concentration values, and that's all the rows in the first column. Oops. And I want to show that plot. And secondly, I'd like to plot all the temperature values, so that's all the rows in the second column. Did I say second first? This is the first column, this is the second column. And I want to show that as well. And let's try and see if that works. Let's try that. Here we have the concentration profile, or rather the concentration development over time. It doesn't quite look like the graph you see in the book, but the graph in the book is actually obtained using a linearization technique. So this should actually be probably more correct. And here we have the temperature profile. Right. That concludes our work with the reactive, closed, and adiabatic system.